Welcome to video number 3, which talks about step number 2 in the organic nomenclature process, which is finding and indicating the parent hydrocarbon. Now, the definition of a parent hydrocarbon is straightforward. It's the longest continuous carbon chain, that contains the functional group. That seems straightforward because it is. If the molecule has an IUPAC functional group, this step should be quite straightforward. I actually can't think of any cases where it's not pretty straightforward. A couple of riders on it. There is a discontinuity between rings and chains. If you are counting along a chain and you run into a ring, you stop. If you are counting within a ring and you run into a chain, you stop. I have examples of both that I'll show you in this video. Hopefully that'll make it nice and clear. Like we have said in past videos, it is entirely possible to have a molecule that contains nothing that IUPAC defines as a functional group. That seems like it would make things simpler, actually makes things harder. We'll go through examples of that as well, but it then would just be the longest continuous carbon chain with a little rider that I'll talk about later. Some examples of that we know are alkyl halides and ethers. Those are not considered functional groups by IUPAC, and they have no influence over where the parent hydrocarbon goes, except when you bury fairly deeply into alkane nomenclature voodoo, which is quite frankly no fun at all. And the functional group can be somewhere in the middle of the parent hydrocarbon. Not for all functional groups. Carboxylic acid is always terminal just by the fact that it has so many bonds to oxygen. Aldehydes, same thing. So nitriles, there are functional groups that are only at the termini, but that's not true of all functional groups. Ketones, for example, can be right in the middle of a chain, no big deal. Same with alcohols and amines. Now, the easiest way to do this, I believe, is by example. So let's go back to our buddy citronellal. Our functional group, as we talked about earlier, is the aldehyde here. Our longest continuous carbon chain would be, starting here at the aldehyde, 1, 2, 3, 4, 5, 6, 7, 8. So I can go that way. One could easily also argue that I could have gone this way, but I didn't. If you remember in the functional group video, I told you that alkenes and alkynes, while they're not IUPAC functional groups, sometimes they can strongly influence the parent hydrocarbon, just like a functional group does. This is a classic example of that. You choose the direction that contains the most pi bonds. There are some nitpicky rules on that, like alkenes are more valuable than alkynes for reasons that nobody knows. Fortunately, they don't come up very often. But if you have a choice with your parent hydrocarbon, choose the one that contains the most pi bonding systems. Now, that cancels out that guy. And we are left with 8. As I'm sure you recall, but I'm going to remind you anyways because it's what I do. 8 is octa. They go by you don't need to know past 12, and even 11 and 12 I have to think about some. That's meth, not really, but we call it meth. Eth, prop, but, pent, sex, sept, hex and hept. Got my Greeks and my Latins crossed. Oct, non, dec, unidec, dodec, tridec, so forth and so on. So for this, we are looking at oct, which is 8. And it is an alkene, which means it's not an ane, it's an ene. So we have an oct in here, we'll have an ene in here, and of course, it's an aldehyde, so al. We also need to pause now and back up the bus a little. That alkene could have been anywhere along this alkyl chain. So we need to tell everybody where it is. You can look at this one of two ways. They give you the same answer because they are basically the same thing. You can count the bonds starting from carbon number 1. So in this case, that would be 1, 2, 3, 4, 5, 6, 7. Or you can say the lowest carbon that's involved in the pi system, which is number 7, is where its position is. In either case, and that's always true, this is a 7 ene. So our molecule, ignoring substituents, which we are until the next video, is an oct 7 ene al. Modern IUPAC, that is where we put the number. We put it right before the thing that it's describing, in this case the alkene. You will often see this shown as something like 7 substituents octene al. That's the old school IUPAC. I don't like it as much because it's harder for you guys. And it's old-fashioned. It makes you sound like a 65-year-old chemist, and nobody wants to sound like a 65-year-old chemist, at least for the next 15 years. So you are allowed to use either one. I'm, of course, quite able to tell the difference between the two. I think you will find it easier if you indicate like this. Now, that one's nice and straightforward. Let's look at, menthol, our mint molecule. This is the guy that's the thing that you taste in peppermint. Not spearmint or wintermint, but peppermint. This is fun because it has rings and chains in it. This is our functional group, as we talked about before. It's an alcohol, so we know the end of this name is going to be al for alcohol, as opposed to al for aldehyde. Our alcohol is on this carbon here. That carbon is part of a ring. If your functional group is directly attached to a ring, that automatically makes carbon number 1 your functional group carbon, unless you have 2 identical functional groups, so if it was a diol. But in most cases, there'll be just 1. You count around the ring in order of lowest overall substituent number. We'll get more into that in the next video. But when we go around this ring, we will never branch out into this set of carbons or the methyl group over here. You will always go around the ring and then stop. So this is a hex, and since it's a ring that's a hex, a 6-membered ring, it's a cyclohex. And that is our parent hydrocarbon for this guy. Cyclo, hex, because there's no pi bonds in the ring system. So it's hexan, all. We don't need to put the 1 in here because it's implicit. Since it's in a ring, it has to be carbon number 1. So there's no point in designating its location. The same was actually true with our aldehyde earlier. Aldehydes are always at carbon number 1. So there's no point in putting a 1 there. Groovy. That was pretty straightforward, eh? Let's go to our friend raspberry ketone. That had an OH here. Now, we got a lot going on here. If you recall, there are 2 potential functional groups, the alcohol and the ketone. Ketone's higher in the list, so it wins. This is our functional group. This is the hard part. the benzene sitting there with that alcohol on it looks really big and important. And to be honest, as a chemist, it is important, not particularly big. But chemistry happens over there. However, stick with the IUPAC definition, the longest continuous chain containing the functional group. The functional group here is the ketone. We know we can't hop from rings to chains because I told you that rule already. So we have a 4-carbon parent hydrocarbon. Does not matter that the benzene is bigger. It doesn't have the functional group. So all right, we have a ketone. We have the choice of numbering it left to right or right to left, 1, 2, 3, 4. You choose the way that gives the functional group the lowest number. So in this case, that's right to left because then the ketone is at carbon 2 instead of carbon 3. So this is a bute, and because there's no pi bonds in it, 2 one, butan 2-one. Again, you could have this as a 2 substituents, butanone. This is old style. This is new style. I don't care what you use, but I think you'll find new is easier. You will certainly see it written in the literature both ways and in your textbook. Well, all right then. That was pretty straightforward. And when you have a functional group, it is straightforward like that until you get to really complex molecules where it's not obvious what is and what isn't the functional group. But like I've said in the previous videos, when they get really complex, we don't very often bother with the IUPAC name. Back when I was in university, we had to because we didn't have the internet, honestly. In that case, we had to look up, if we wanted to find a paper on a particular molecule, it was alphabetical by its IUPAC name, and you had to be really good at it. We don't have to be that good at it in this day and age. We have computers, we have structure searching. We just need it to be good enough that we have a common language together. So that if I tell you we're going to be doing reactions on 2-butanone, or in this case, a derivative of 2-butanone, we don't have to sit down and draw structures every time. You could immediately write down what 2-butanone is. Actually, 2-butanone, as it is redundant because it has to be a 2 in butanone. Let's try, I almost hesitated doing this because it's not very common, and I know you beat it to death in high school. But if you're naming something that has no functional groups, that is strangely harder than naming stuff that does have functional groups. I'm not going to get into the arcane details of alkane nomenclature because in case you manage to forget it, it's horrible. Like nightmares still 30 years later, horrible. But there are some simple rules that can help you out with molecules that aren't huge and designed to be confusing. So simple alkane, we'll take a benzene ring and we'll put a chain on it, like so. Those guys are connected, though my pen doesn't seem to want to. Now, rings and chains are separate, and we are looking for the longest continuous carbon chain. We have many possibilities here. We have 1, 2, 3, 4, 5. We have 1, 2, 3, 4, 5. We have, oh, green's a pretty color. 1, 2, 3, 4, 5, 6. I can never cross this magic wall between the ring and the chain. So there's no point even in trying. In this case, I think it's fairly obvious the benzene ring wins. Benzene is a special alkene name, and we do not call this cyclohexatriene. It's even hard for me to say the words because I maybe have never said it before in my life. We'll talk a lot about benzene in the second term. There are a lot of reasons why it's special, and you've brushed across those reasons both in high school and in first year. But we'll get into more detail as to why that's such a special thing, though you really don't get enough detail on why it's awesome until you've done quantum. But I'll do my best next term to make it interesting. So this guy wins. The parent hydrocarbon is benzene. This would be an alkyl benzene. If you recall, alkyl halides, despite the fact that they are where chemistry happens, also don't determine who is the parent hydrocarbon. Now I'll just put, this is not a real molecule, but alkyl halides are boring. Why not put unreal things on it? Well, let's put another fluorine in. That always scares people. Okay, here we have a typical first year nomenclature problem where they are trying to trick you. Let's keep in mind we have our potential for discontinuity here. This guy has, as benzene always does, 6 carbons in it. Other possible chains here would be 1, 2, 3, 4, 5, 6, 7, 8. I just instinctively took the longest one I could there. We could have done some silly things like called that carbon 4, but obviously that adds up to 4, or 2, 3, 4, 5, 6, 7, or 1, 2, 3, 4, 5, all of which are silly answers. Same thing with this potentially being 6. But our winner here is clearly this long alkane chain, despite the fact that my benzene ring is so beautifully decorated with all these gorgeous halides, unreasonably decorated with gorgeous halides. But this is an octane. Yeah, that's pretty much it. There is not a lot of subtlety to finding the parent hydrocarbon with most molecules, as long as they have a functional group. Again, like I said, with apologies, because I know you've suffered through it before. If it's a pure alkane, an alkyl halide, or an ether, those can be a little bit tricky to sort out. But we don't have to do it very often. So our next video is going to be on taking all the stuff that we haven't described yet. So everything that is not the functional group or the parent hydrocarbon gets described in substituents. And that only leaves us 2 videos left of this series. Well, actually, it's going to be more than that, because I'm going to have 1 video of things that are kind of hard to name, like esters and amides, and ethers are also hard to name. And then another one of just various examples so we can have nomenclature joy together. But in the core videos, there's just 2 more to suffer through. I am aware that nomenclature is perhaps not the most interesting thing in the world, to say the least. So I will try to make them short. All the best, and until next time.